Hey YouTube, welcome back. Today we continue our series in design consistent hashing. In the previous video, we talked about why we need a consistent hashing, and we talked about the rehashing problem. And we said that if we have these servers and we have like 4 servers and we have this hash number of each one, and we loop them, we just run the hash key function over the server sizes. The server pool size, we get specific numbers, and we get like each client has a server, and this will go well. However, when we change one of the servers, or like if one of the servers will be offline, or if we add one server, that means the server pool will increase or decrease. Like for example, the server pool decreases right there. And as you can see from this example, before server 1 has full, we had server 0 has like client 1 and 3, server 1 has 0 and 4, server 2 and 2 and 6, server 3 has 5 and 7. When server 1 has full, we had a lot of problems. One of them, that all the clients redistributed to new servers. That means that all clients loses their cache. And the second thing, that we have some servers, like number 0 has 4 clients, and maybe the other has 2, so there is no distribution in the actual in the hashing. So we still got this problem, and we solve this one by using something called a consistent hashing. And we talk today about something called a hash ring. So in order to talk about the hash ring, let me just, because it's a ring, let me just put a circle here. I guess we need to make it big. Let's make it big. Yeah, just make it, can you? Yeah, okay. So what is a hash ring? First, a hash ring, also known as a token ring or consistent hashing ring, is a data structure used in distributed computing and data storage system. It plays a crucial role in implementing consistent hashing, a technique for efficiently distributing data across multiple nodes or servers while minimizing the impact of adding and removing nodes. The hash ring is a visual representation of the consistent hash space, and helps determine which node is responsible for storing or handling a particular data item. So basically, let's say that this is the hash ring, and this we want to represent the consistent hashing in it. And the consistent hashing is a technique used in distributed computing and data storage systems to efficiently distribute data across multiple nodes or servers while minimizing the impact of adding or removing nodes. And it's particularly useful scenarios where the number of nodes can be changed dynamically, such as distributed databases, for example, or distributed system. And yeah, this is the main thing. So basically, we have a problem with the previous hash. When we change the pool size of the servers, we lose all the clients are redistributed to a new servers. So that means we lose the cache of the servers. Maybe we have some servers have a high load on them, and the others have like too little load, or like too little pressure on them in the traffic, and it looks like chaos. So hash ring used to solve like that. So let's say that, imagine we have this ring, this we call a hash ring, and let's just place our servers like that. Let's say that we start with 4 servers, okay, servers, and let's say that we have 4 hash keys, for example, and each key represents a client. So let's just make it like that, and we have like 4 hash keys. Let's see, let me no, looks ugly. So yeah, let's see that we have 4 hash keys. Okay, and and basically determine which server a key is stored on. We go clockwise from the key position on the ring until the server is found. So for example, we have this one, we go clockwise, so we have the logo like that. So let's say that this is S1, this is S1, this is let me take a text for that. Let me just this is S1, and this is S2, and this is S3. Oh, it's S3, and this is S4. Okay. And we have 4 servers and we have 3 keys right now, and this is Q1. Can I make it red, please? This is Q1. This is Q2. And this is Q3. Let me put inside. And this is Q4. No. Okay. So yeah, let's see. So basically, we go clockwise to know each key which will be stored in for which servers. Let's just make it yeah, Q1. Oh, okay, it will be like, okay, let's just start it like that. We have this will be Q2. Okay, this let's continue. Okay, so Q1 will be stored in server 2, and Q2 will stored in server 3, and Q3 will stored in server 4, and Q4 will be stored at server 1. Okay, so let's say that we have we want to add server. We said that in the previous video that the rehashing problem, that when we would change the server size or adding more servers or removing more servers, that could lead to a problem. So let's just add a new server. So let's just add new server here. Let me take a color. Let's say that I'm adding a server here, a new server here. So basically, in the previous example, when we add a new server, all the clients change their server and change their cache. But in this one, this doesn't happen like that. So let me just try to remove this one. What happened? That server 1 will the key 4 will connect with this server 1. Let's just call this server S5 and make it color okay. So basically, key 4 will connect directly with server 5. So let's delete let's remove a server. For example, let's just remove the server 2. Okay, to see how this will work. Let's just remove server 2, and yeah, we have no server 2 right now. So what will happen is that server 1 will be connected with server 3, which is this one. So I don't know if you can understand it or not. So when we add a server in the hash ring, the only client was affected was the key 4. This is the only one where we changed its position, and the all other keys, they have the same connection with the servers that they were connected to. The Q1 had the same thing. The Q1 was connecting with server 2 when server 2 has been like fall down or been removed. It connected with server 3, and none of the other keys has been affected by that. So it looks quite working. However, we have two issues in this basic approach. The consistent hashing algorithm was introduced, like I guess, at the MET. So basically, the basic steps, it was pretty basic. So basically, map servers and keys on the ring using the uniformly distributed hash function, and to define out which server is mapped to which server is mapped to which key, we go clockwise from the key position. Two problems are defined with this approach. With this approach, the first one, it's impossible to keep the same size of the partition on the ring for all servers, considering a server can be added or removed. A partition is the hash space between the adjacent servers, and it is possible that the size of the partitions on the ring assigned to each server is very small or fairly large. For example, here this is one. It's really small. From key 1 to key 3 is to S3 is really large. So this is one of the problems. And also it's possible that the size and also when we remove a specific when we remove the second thing, it's possible to have a non-uniform distribution on the ring. For instance, if you can see here, server 1 has no traffic, nothing, and server 3 has 2 keys in it, and this and this one leads to a lot of problems. And a way to solve this one, we use something called virtual nodes, and a virtual node refers to the real node, and each server is represented by multiple virtual nodes on the ring. So basically, instead of having, so for example, instead of having only server 1 is represented by one position, we add another position to server 1. But let me just delete some stuff here, so it will be for us easier to us to let me delete this and delete this, and I want to delete this, and I want to delete this, and yeah, can I copy this? So let's say that we have server 1 here, okay, again, and we have let's just oh, sorry. Let's have server 1 here, for example. Okay, I'll do something. Okay, let's just delete all of that. So let's say, let's have a pen. Yeah, so let's say that we have server 1 here, and we have let's say that we have no server 3 anymore, and we have server 3 again here, and maybe we have server 4 again here, and let's add more keys, and just have like that, like that, like that, like that, and so on and so forth. So basically, by using the virtual nodes, we implement, like, let's say that this is, let's just add the text, because with the text it will be good. It will be server 1 also here. This will be server 2, this will be server okay, I did this problem. Let's just delete this one, and this will be server 2, for example. And yeah, so we're using something called a virtual node, and a virtual node refers to a real node, and each server is represented by multiple virtual nodes on the ring. So as you can see here, server 1 is represented by multiple server virtual node, and server 2 is represented by multiple server nodes on the ring, as you can see here. So both server 1 and server 2 nodes, right, I give it 1 and 2, right? 1 and 2, yeah, 1 and 2 is represented more than one time. The sorry, I just sometimes I lose focus. So the good thing about this one, we make sure that all servers getting the all the traffic, and we redistribute the traffic and make them sure the traffic evenly. Another thing that good, that if we know that server one, for example, has a lot of ability to handle load balance more than maybe other servers, we can just implement more of the positions that refers to S1, and in the same as S2 and S3. So to find which server, so basically, with the virtual nodes, each server is responsible for multiple partitions, because right now S1 has multiple partitions here, with the labels like S1, S2, S3, etc. And to find which server is stored on, we go clockwise. So basically, if we go into like that, it will be stored here, where this one is stored here. For example, we can maybe add another one here, so it will be stored here, for example, like that, and just one here. Let's go back because it's looking like a mess right now. So this one will be here and will be here, and we'll just try to add virtual node when we find that there is uneven partition, or like uneven load, and we just have, oh, this is not right, and let's just add a new key here, and let's just add it like that here, and that, and so on, so forth. Oh, bad. Okay, and so on, so forth. Let's just delete this one. And as I said, though, to find which server a key is stored on, we go clockwise from the key's location, and to find this first virtual node encountered on the ring, as you can see here, to find out which server S1 or K1 is stored on, we go clockwise from example, where is example K1 to S1, from example, which refers to server 1. As the number of virtual nodes increases, the distribution of keys becomes more balanced. This is because the standard deviation gets smaller with more virtual nodes, leading to balanced data distribution. Standard definition measures how data are spread out, and to outcome, an experiment carried out by online research showed that with 1 or 100 virtual nodes, the standard deviations is between 5%, 200 virtual nodes, and 10% in 100 virtual nodes. Of the mean, the standard deviation will be smaller when we increase the number of the virtual nodes. However, more spaces are needed to store data about virtual node. This is trade-off, and we can tune the number of virtual nodes to fit in our system requirements. The other thing we want to talk about is to find affected keys. So when a server is added or removed, a fraction of the data needs to be redistributed and redistributed again. How can we find the affected range to redistribute the key? So for example, let's say that we this server has removed. Okay, so we need to know how to find it and how to do that. So how to find how to redistribute it. So as you can see, so server, we have like server 1 or server 4. Server 1 is removed from the ring. One of the virtual nodes of the server 1 is removed from the ring. So the affected range starts from S1 to S2, like it starts in this range, specifically at K1, and we move clockwise from K1 to S2 to find the first virtual server, or the first node, and we find S2 and we store it there. And when we add a new server, so let's say that we add a new server here. So for example, we adding a new server here. one like that. Okay, this doesn't make any sense. Let's just add one different place. Yeah, let's add it back. So let's say that we add a server back. So when we add a server back, we know which range has been affected, and we basically, okay, this is not the color for the servers. Yeah, let's have this one. Yeah. So basically, let's add a new server here, and when we add a new server here, instead of K1 connecting with S2, K1 will go clockwise. K1 will be connected with S1. So this is what happened when we removed or add the servers. And let's just make a small wrap up, because this is the consistent hashing. So in these two videos, we had in-depth discussion about the consistent hashing, including why it is needed and how it works, and the benefits of the consistent hashing, including the minimized keys are redistributed when servers are added or removed. Second, it is easy to scale horizontally because data are more evenly distributed. Third, mediate hotspot and key problem. Excessive access to a specific shard could cause server overload. Imaging data for example like Katy Perry or Justin Bieber and Lady Gaga all end to the same shard. Consistent hashing helps to mitigate the problem by distributing the data more evenly. Consistent hashing is widely used in real-world systems, including notable ones. So we have the partitioning component of Amazon Dynamo DB database, the data partition across the cluster in Apache Cassandra. We have Discord chat application. We have the Acme content delivery content. We have the maglev network load balancer. So it's used in a lot of well-known applications. So this was what is the consistent hashing all about. And I hope that you like my content. And if you like my content, make sure to subscribe and hit the notification bell so you will never miss a good video. And I hope that I'll see you in future problem, guys.